Here's an integral that we can solve by substitution. In the exercise where this is given, they give you a substitution, let x equal 4 sine theta. And so we're going to use this in order to evaluate this integral. Now, once you have a substitution, you've got to obviously start by working out all the pieces that are going to fit into here based off of this. So some easy examples. First, you can see that there are x squareds here, and I've got an x, so I'm going to need to work out what x squared is, which is not hard. It's 16 sine squared theta. At the same time, if I want to do the substitution, I'm going to need to know the derivative here. So that's dx on d theta is 4 cos theta. So you can see that dx there is going to substitute for a 4 cos theta d theta. Okay, so far so good. Now I can start to put these pieces in over here. So what do I get? Well, the integral of, now you've got 16 minus 16 sine squared theta. Up on the top, that's what we just determined over there. On the bottom, you've got 16 sine squared theta, because it's just another x squared. And there, instead of dx, I'm going to write 4 cos theta, d theta. So there you go, I've done all my substitutions. So far, so good. But we can do a lot of simplifying here. For starters, what's underneath this square root sign here is a 16 cos squared theta using the Pythagorean identity. Then you've got a 16 sine squared theta still there times 4 cos theta. Alright, so you can see a few things here. That 16 under the square root is going to become a 4. Together with that 4, there'll be 16, and there's a 16 on the denominator. So I'm going to cancel all of those coefficients. That's kind of nice. Secondly, I've got the square root of cos squared theta, which, properly speaking, is the absolute value of cos theta. And then you've got another cos theta there. So you've got cos squared on the top, sine squared on the bottom. Okay, now you have to think about what you can do with this to make it better, and there's an identity, a very simple identity, again the Pythagorean identity, which will help us here. On the top, that cos squared we can write as 1 minus sine squared. The reason why that's useful is because it'll let us cancel very simply with what's on the denominator. I'm going to get 1 on sine squared minus 1, and all of that is integrated with respect to theta. Okay, now this is good. This is better than what we started with. I know how to deal with that 1, but that's 1 over sine squared is a little more finicky. So how do I deal with it? Well, you can do this if you can't see the result straight away. You can do this by t results. We've learned how to do integration by t results, but it's not complicated enough to really warrant that. If you can see that, what I can do here is divide the numerator and the denominator by cos squared. Now, if I do that, the reason why that would be useful is it turns the top into sec squared, and it turns the bottom into tan squared. Okay. Now this is nice because sec squared is the derivative of tan, so this sort of fits into a reverse chain rule, and this is really sec squared times tan to the power of -2, and then of course we have our -1 there. Right? So what you've got here is a function raised to a power, and you've got the derivative of that function on the outside. So you can see that you would get this result if you differentiated something and used chain rule, but we're going to do it in reverse. Okay? So what do we get here? This is going to be equal to, you take that function, you raise its power by 1, but you're also going to divide by that new power. So you're going to get negative tan theta the power of -1, and then you should have divided by the derivative of the inside function, which is sec squared, so it just disappears, it cancels. There you go. Then you got minus, and that -1 turns into a theta. Okay, so what you've got here, this is actually negative cot theta minus theta. This is good, but our original question had nothing to do with thetas. Sorry, I should have added the constant in there. The original question had to do with x's, right? So just like I got rid of the x's and put them in terms of thetas, I should do it in reverse to get it back in terms of x's. So the question is, what can I do with these? Well, the theta is easier to resolve. If you have a look at x equals 4 sine theta, I can make sine theta equal to x on 4 by dividing both sides by 4. And that gives you this result. theta is sine inverse of x on 4 in a restricted domain anyway. So therefore, I can use that to substitute for this theta. But what do I do with this cot theta? That's a bit of a pain. Well, we can still work with it if we come back to this line. Sine theta equals x on 4. Now, again, in a restricted domain, we can consider theta as an angle in a triangle, specifically a right angle triangle. So if I stick theta over here, if sine theta is x on 4, that means that the opposite side on the hypotenuse, opposite on hypotenuse, that should be x on 4, right? Now that makes my Pythagoras, this side over here, 16 minus x squared. So if I want cot theta, that's going to be not opposite on adjacent, which is tan theta, but adjacent on opposite. This over that, that's cot theta. So therefore I can substitute that in. That'll be negative the square root of 16 minus x squared all over x. And then I said that I was going to substitute theta for sine inverse. Minus sine inverse of x on 4 plus your constant. And there you go.